It's my great pleasure to give a talk here in IPAC seminar. Personally, I learned a lot for the IPAC seminar in last 2 years, so it's very honored to give a first talk in IPAC seminar this year. And thank you everybody for coming to hear this, no matter what time zone you are. And as introduced, I'm gonna talk about my preprint towards Butler's conjecture, and it's based on the joint work with Dong-Young Kim and Seung-Jin Lee. Okay, so since I graduated, my research was concerned in McDonald polynomials. Oh, and today's talk will be very introductory, and I'm not going to define everything, but if you have any questions, please interrupt. And for starting from the next lecture, I will give precise definitions and give you as many examples as possible. But for today, I'll keep it concise. Okay, so there's many bases like monomial bases, elementary symmetric functions, homogeneous symmetric functions, and power symmetric function. These are all bases of the ring of symmetric function. And one of the most important bases is a Schur function. So Schur function, and I'll denote it by S mu. And in 1988, McDonald introduced a QT generalization of the Schur function, which we now call McDonald P polynomial, denoted by P mu, which is a symmetric function and whose coefficients are a rational function of Q and T. And by rescaling it, we get McDonald J polynomial, J mu, whose coefficients are polynomials in Q and T. So sometimes, that's why sometimes we call this as an integral form. The polynomiality is not trivial at all. But a few years later, McDonald defined the McDonald J polynomial. The polynomiality was proved. The more difficult question was McDonald positivity conjecture. So for a partition mu, let J mu is expanded into the Schur function, but with this platistic substitution. And let the coefficients be K lambda mu. Q
You mean S lambda?
Oh, sorry, S lambda. Thank you. And then the coefficients K lambda mu Qt, which is called the Qt cos cut polynomial. The conjecture asserts that these are in NQT, so it's a polynomial in Q and T, and the coefficients lies in the coefficients are non-negative integers. And Garcia and Heyman introduced a little different version of it, introduced the modified McDonald polynomial. Okay, polynomial H tilde mu by H tilde mu is defined by a platistic substitution to McDonald J polynomial, 1x over 1 minus t, qt, and then take t reversal. Then you get the modified McDonald polynomial. And the McDonald positivity conjecture can be rephrased with this modified Macdonald polynomial. So let mu be a partition. Then, and suppose we have a sure expansion, actual sure expansion of this modified Macdonald polynomial, and denote the coefficients by k tilde k, lambda mu of qt, sure function. Then these coefficients, k tilde k lambda mu qt, sometimes called modified Macdonald, modified qt-Koska polynomial, but sometimes we just call it qt-Koska polynomial. These are in nqt, so it's a polynomial in qt with non-negative coefficients, non-negative integer coefficients. So far, so good. And oh yeah, I had a COVID almost a week ago, so my voice can be weird, so please understand. And to prove the Macdonald positivity conjecture in this sense, so it's proving a sure positivity. So one may seek for a representation theoretic model or SN symmetric group representation. So to construct such a model, Garcia-Heyman defined so-called Garcia-Heyman module indexed by partition mu. To define, let delta sub mu be the determinant of an n by n matrix where mu was a partition of n. So xi to the co-arm of a cell and yi to the co-leg mu of c, and where I runs through 1 through n, and c is a cell of mu. And this one should sits inside the polynomial ring of 2n beta group, x1 through xn and y1 through yn. And recall that co-arm and co-leg, recall that if you have a cell C here, so these are a partition mu in a French notation, the length of this is called arm mu of C, and this is called leg mu of C. And this one is called co-arm and co-leg mu of C. So these are the data comes from these two length or the number of cells. So for example, del 2, 1, if you draw a Young diagram of 2, 1 and record the co-arm and the co-leg, it's 0, 0. For this cell, it's 1, 0. For this cell, it's 0, 1. So delta sub 2, 1 is a determinant of 3 by 3 matrix. And the first column will index the information of the first cell, which is 0, 0. So x to the 0, y to the 0. So it's 1, 1, 1. And second column will encode the data of the second cell. So it's x to the 1, y to the 0. So it's x. So x1, x2, x3. And the last column will be y1, y2, y3. And if you calculate this, however you want, it will give x2, y3 minus x3, y2 minus x1, y3 plus x3, y1 plus x1, y2 minus x2, y1. Okay. And the Garcia-Heyman module, V mu is defined as a span. So V mu is a span of partial derivatives with respect to x1 through xn and y1 through yn, partial derivatives of the polynomial delta sub mu. So inside the polynomial ring of 2n variables. Okay, so let me give you an example. So V21 is span of, okay, delta 21. I've calculated here. And you can take partial derivative with respect to y variables. So take partial y1, it will give, okay, so x3 minus x2, x3 minus x2. And partial y2 will give x1 minus x3. And if you believe me, I'll just write down all the partial derivatives. x2 minus x1, x1 to 1 is y2 minus y3, del x2 is y3 minus y1, y1 minus y2. And if you take partial derivative twice, you will end up with 0 or plus minus 1. So partial x1, partial y2 will give 1. Okay. First thing you can notice is that these three are linearly dependent, and these three are linearly dependent, and actual dimension is 2 for this one and 2 for this one. So the whole dimension of the Garcia-Heyman module V21 is 6. And you can also say that 6 is a vector, 3 factorial. 6 can be anything, but we know 6 is a 3 factorial, so I'll just write this way. And also note that the Garcia-Heyman module V21, Garcia-Heyman module V mu is not just a vector space, it's is a bi-graded, so there's a grading x and y degree, total degree of x and total degree of y, and it is an SN module where SN action is a diagonal action. So sigma acting on xi is a x sigma I, and sigma acting on yi is y sigma I. So it's diagonally permuting variables. In this sense, okay, we can since it's bi-graded. First, we can say the Hilbert series of V21 Qt. So this one is of degree 1, 1. It has x and y. And this is of degree 1, 0. And these three or two-dimensional subspace is of degree 0, 1. And the last one is 0, 0. So we can encode this in the Hilbert series as qt plus 2q plus 2t plus 1. Moreover, since it is an SM module, and there's a way to associate a symmetric function to each of SM module, it's called the Frobenius characteristic, which associate a symmetric function for each SM module by taking the irreducible representation indexed by lambda partition lambda, sometimes called the spec module, to the Schur function indexed by the same partition lambda. And by taking this Frobenius characteristic, you can say that the graded probabilistic characteristic of V21 Qt is okay. So for the degree 1 part, since this is a determinant and SN action permutes the columns because it permutes the coordinate, so it permutes the column, so it gives a sign. So the degree 1 part is a sign representation. And if you are familiar with this, you can see that these two-dimensional vector spaces or submodules are irreducible representation S21. This one was S111. And for the scalar, it's the SN action do nothing, so it's a trivial representation, S3. So in the words of graded Frobenius characteristic, you will have SQT times S111, Q plus T times S21 and S3. And I haven't calculated any of McDonald polynomials, but if you believe me, this is a modified McDonald polynomials of 2, 1. And these two equation was observed by Garcia and Heyman and eventually proved by Heyman. So Heyman in 01, it's sometimes it's called n factorial theorem, and it was conjectured by Garcia and Heyman in mid-90s. So 93 paper or 96 paper. It states that for partition mu of n, we have the dimension of the Garcia-Heyman module is always n factorial. And the graded Frobenius characteristic of the Garcia-Heyman module is the modified McDonald polynomial. So in some sense, Garcia-Heyman gave a representation theoretic model for the modified McDonald polynomial. And as a side note, if you specialize Q and T with 1, you will get the H1 to the N. So as an ungraded SM module, Garcia-Heyman module is always isomorphic to the regular representation. And anyway, since the modified McDonald polynomial came from a genuine SM representation, we can conclude that the modified McDonald polynomial is sure positive. So this theorem established the McDonald positivity conjecture. And Heyman proved it using geometry of Hilbert schemes of endpoints in a plane, which I don't know much about. And his proof was geometric and did not give a combinatorial recipe to find the Qt coscat polynomials, which was a short coefficient. So it is still a major open problem, is that to find a combinatorial interpretation of the short coefficients. So k tilde lambda mu of Qt. Since it came from the regular representation, we know that k tilde lambda mu sub 1, 1 is a number of standard tableau of shape lambda, no matter what mu is. So maybe we want a formula that looks like this. So over standard tableau q to the some kind of inf statistic. No, I'll just say stat q of t and t to this, that t of t, yeah. We may want to find a formula of this particular form, but in any sense, we don't know the combinatorial formula. Okay. Is there any question so far? Okay. To prove prior to the solution of Heyman, to prove the n factorial conjecture, François Bergeron and Garcia studied science fiction conjecture. And if you read the paper, the science fiction conjecture is cannot be described in few sentences. I think the conjecture is 1 page or longer, and to understand the statement in that page, you have to read all the other pages. So it is not very concise, but there's many things to explore. But I'm gonna focus on 2 implications of the science fiction conjecture. To describe, let's say, let mu be a partition of n plus 1, and mu1 through mu k be a subpartition of mu. They're all distinct. So k distinct partitions such that the difference of the size are all 1. So mu minus mu k is 1. So in other words, we can obtain each mu k by removing a corner of a given partition mu. So for example, mu can be this shape, 3, 2, 1. And we can take mu1, mu2, and mu3 by excluding these cells. So mu1 by this one, mu2 by this one, mu3 by this one. Okay. And you can say that all these mu1 through mu k's are similar in some sense, or you can obtain one from another by removing by moving a cell. To obtain mu2, we can move this cell to this place, or move this cell to this place. So in some sense, these mu1 through mu k's are similar. And science fiction conjecture concerns the Garcia-Heyman module of these similar looking partitions. So if you calculate the Garcia-Heyman module of V mu1, V mu2, V mu3.
Question for you. Question.
Okay.
Those removable, there must be some condition on which corners are removable, right? It's not any corner, right?
Oh, you can remove any removable corners.
So you have to define what removable corner is.
Oh, yeah. Oh, okay. Removable corners are cells. It is a cell that if you remove that cell, it's still a partition. It is still a partition. So you cannot remove this one.
Thank you.
Okay. Okay.
Thank you.
Okay. Thank you for the question. And okay. Science fiction conjecture concerns the intersection of these Garcia-Heyman module, or the sum of these Garcia-Heyman module, and yeah, anything you can see in this Venn diagram. Science fiction conjecture concerns all of it. And as I said, the two implication of the science fiction conjecture is Bergeron Garcia in 1909. First one is called n factorial over k conjecture. Recall that dimension of a single Garcia-Hamilton module is of dimension n factorial. And what science fiction conjecture imply is that if you take the intersection of Garcia-Hamilton modules, mu1 through mu k, then the dimension of this intersection is n factorial over k. That's why we call this conjecture n factorial over k conjecture. And if you, it also conjectured that we can calculate the gradient Frobenius characteristic of this intersection in a very precise way. So it's a sum of modified McDonald polynomials of mu I with weight given by Tj, I mean T mu j over T mu j minus T mu I, where j is not equal to I. And here, okay, where T mu is product of Q to the coarm and T to the coleg over all cells in mu. And the right-hand side, we will define this as a I mu1 comma mu1 da 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 mu k, and call this symmetric function as McDonald intersection polynomial. Okay. So once again, I will give you an example. Recall that the Garcia-Hamilton module of Q1 was a span of delta sub 2, 1, x1 minus x2, x2 minus x3, y1 minus y2, y2 minus y3, and 1. And this gave us a McDonald polynomial, qt times s1, 1, 1, q plus t times s2, 1, and s3. Okay. To give you an example, for the science fiction conjecture, we need a similar looking partition, and let the partition be 3, the one row partition. So V3 is span of delta sub 3.
Can I ask a question?
Yeah, sure.
On your previous last page, you erased. Yeah, here, I'm just curious about one thing, and that is, if you do on the graded Frobenius, Q and T equal to 1, then on the right-hand side, the denominator vanishes. So
Yeah.
what is stabilizing it?
What was the question? Last sentence?
The denominator will be 0. So what's canceling that singularity? Okay, do you see the product there? The product?
Well, it's a sum of rational functions, though.
Yeah. But at last that the all the coefficients cancel, and you will get polynomial. I mean, the coefficients will be polynomials in Q and T. You will see in this example how this happens. Okay. And Garcia-Hamilton module V3 is, you have to believe me with this calculation. This one is a van der Monde determinant, and if you take a partial derivative, you will obtain something like this: x2 minus x3, 2x2 minus x3 minus x1, x3 minus x2, and x1 minus x2, x2 minus x3, and 1. Okay, so the McDonald polynomial will be, this one is of degree 3, 0, and these two are of degree 2, 0. These two is of degree 0, 1, 0, and 0, 0. So, and these two forms S21, and these two, forms S21. So the graded Frobenius characteristic gives Q squared S111. No, QQ. Q squared plus Q times S21 plus S3. And if you calculate, if you want to check the science fiction conjecture, you take intersection of these two Garcia-Heyman modules. You see that these two are the same, and of course the scalar is the same. So this will give you 3, which is 3 factorial over 2. So it's compatible with the n factorial over k conjecture. And you can calculate the graded Frobenius characteristic. On one hand, you can calculate it with these data. So take intersection. So the same parts are here. So it will give Q times S21 plus S3. And on the other hand, we can calculate the McDonald intersection polynomial mu2, 1, 3, which was defined by T3 minus T21, T3 times H21 minus T21 times H3. And T3 is 1 times Q squared, so it's Q cubed. And T21 is 1 times Q times T, so it's QT. And in this calculation, you can see that this is a ratio QT versus, QT versus QQ. And this one too. So it's T over Q squared. So it's same as QT over Q cubed. And since we multiply this T3 and T21 and taking subtraction, all these blue terms vanishes. Okay. And since for the red terms, these are the same. So multiplying these and take subtraction and dividing by this will give you the same thing. So you will end up with QS21 plus S3, which was given by, and this was expected by the science fiction conjecture. And you may wonder why this happens, and Butler was the one observed. There might be a simple way to obtain a Macdonald polynomial from another Macdonald polynomial by exchanging these terms. I mean, we couldn't figure out yet, but maybe there's a way. I'll explain the Butler's conjecture later. Before I go to the Butler's conjecture, I'll introduce the HHL formula.
Excuse me. Can you repeat what you said as being the relationship between the H tildes, H21, H3? You just mentioned interchanging something.
Oh, yeah, okay. So there might be a way. I mean, so these coefficients, I mean, these terms are the same. So if you know how to get the same terms and get the other terms that are not the same, but you know that the ratio should be Q cubed over QT. So if you know all the terms and all the information, you can just exchange this term with QT and exchange this term with T, then you will get the new Macdonald polynomial H21.
I see. So
Yeah.
are you trying to see if you can get all of them from one of them or what? All
Can
the-
I understand?
Okay, what I'm saying is you could do, you want to connect H3 and H to 1. I see
Okay,
that.
yeah.
And are you trying also to do H3 connected to H111 in case?
Oh, yeah. Okay. Oh, okay. Okay, as I said, science fiction conjecture concerns partition which are similar or partition two partitions, and one of them can be obtained by moving a cell from the other one. So um, if we know all this information, we can always think of this. So from a one row partition, we can move a cell to obtain this one. And any partition can be obtained by moving a cell one by one like this. So uh, um, uh, if we know all the information, we don't know how to track all the information directly, but there's a way to obtain this partition by moving a cell one by one. So yeah, that's what I'm saying. We
Right.
cannot obtain the partition 111 directly from partition 3, but we can move this cell here to obtain 2-1, and we can move this cell here to obtain 1-1-1. The ratio will be different, but maybe
Yeah,
there's
thank
no. Okay, thank you. And as I mentioned, there's no combinatorial formula for the Shor coefficient of the McDonald polynomial, but one of the most important result in that direction, I mean, to give a combinatorial formula, is a Hegland-Heyman-Lohr formula. So for partition mu, we have fundamental quasi-symmetric expansion, or we can give a monomial expansion too, but I'll just mention the fundamental quasi-symmetric expansion. It's sum over q to the inv mu and t to the match mu in fundamental quasi-symmetric function f of inverse descent of sigma, and the sum is over all permutations, so it's over all n factorial permutations. And I'm not going to define these two mysterious functions yet. I mean, I'll define it in the next talk. But for today, you can just think of it as there's a way to generalize the usual inversion statistic and the major index for words or permutation. And our theorem, in me and myself, is concerning this situation. So for our partition nu, and take partition lambda and mu inside nu such that nu minus lambda and nu minus mu is 1, then we can consider the McDonald intersection polynomial I lambda mu, and we found that this can be very similarly described. So it's q to the inv mu and t to the match mu and f inverse descent of sigma, where the sum is over a certain set of permutation, which we call Butler permutations. And this is of size n factorial over 2, as expected in the n factorial over k conjecture. And why we call this paper toward Butler's conjecture, this is because Butler, before the science fiction conjecture, she observed that the same observation I made here. So there might be a way to obtain one McDonald polynomial from another in a very nice way. And she conjectured that the McDonald intersection polynomial of lambda and mu, which was T lambda minus T mu, T lambda H tilde mu minus T mu H tilde lambda, is sure positive. And one remark I want to make is science fiction conjecture implies the Butler's conjecture. Because science fiction conjecture says that this McDonald intersection polynomial comes from a intersection of Garcia-Heyman module, which is a genuine SN representation. So the McDonald intersection polynomial or this I lambda mu should be sure positive. But since we don't know about the science fiction conjecture, we can ask whether we can prove Butler's conjecture on its own. And our next theorem is a partial progress on that direction. So Kim, Lee, and myself, in the same paper, in the same situation, we have proved that I lambda mu is sure positive if the cell we excluded, I mean, nu minus lambda is in the first row or the second row of nu. So for plurally, so this is nu. Okay, these are in the second row. So 1, 2, and consider by removing this cell we obtain mu, and removing this cell we obtain lambda. Then the McDonald intersection polynomial of lambda mu is sure positive. And we also prove I lambda mu is always sure positive without these conditions on the partition, but we have to specialize t equals to 1. Then it is sure positive. And if you are familiar with the QT symmetry, you can also prove 1t is sure positive. Okay. And our next theorem, which is I recall that the McDonald intersection, McDonald polynomial, when you specialize q and t equals to 1, you always have h 1, 1, 1, 1, 1, which was a regular representation. I mean, the Frobenius characteristic of it. And the same thing happens in McDonald intersection polynomial of 2 partitions. So if you specialize qt to the 1, you will always obtain h2 1, 1, 1, 1, 1, 1. And yeah. And last but not least, we gave some combinatorial formula for the qt Koska polynomial, which is compatible with Butler's conjecture. For lambda is hook shape, or mu is a hook shape, or mu is a 2-column shape. And I have to mention that after we, so for the hook shape, we found the formula of Semi-Asaf, and Semi did not recognize this. Her formula was compatible with the Butler's conjecture, and we proved it. So that is our contribution. And for the 2-column shape, we found a new formula. We thought we had found a new formula, but after we write down our paper, we noticed that Mike Jabrocki had a paper concerning the combinatorial formula for Qt-Fosca polynomial, where mu is a two-column shape, and we found that his formula is equivalent to our formula. So, but yeah, I'll explain in the last talk about this formula. And oh, and I have to mention that Alexander Better, who is a student of Jim, and he is in the audience, he is trying to generalize this to thing for mu is combining two column and hook. So it's M to the A, 1 to the B. So in this shape, and he's trying to give a combinatorial formula for Qt-Fosca polynomial when mu is of this shape, which is compatible with the Butler's conjecture. Okay, so this is all I have for today. And for the last 10 minutes, since I have time, I'm gonna promote our new result, which concerns the shuffle theorem. So to state, I have to define some things. So the diagonal covariance algebra or ring is defined as a quotient of a polynomial ring of two n variables. And recall that we had an Sn action on this polynomial ring by permitting variables diagonally. And we take the invariant part and take the quotient. And we define the quotient to be the diagonal covariance algebra. And a theorem of Heyman, again, in 2002, sometimes it is called n+1 to the n-1 theorem, because it states that the dimension of the diagonal covariance algebra is n+1 to the n-1. Okay. And if you are familiar with this number, you may think of KIAS theorem, the number of spanning trees, or the parking function. And I'll explain later where parking functions comes in. And he also showed that the graded Frobenius characteristic of this diagonal covariance algebra is nabla sub En, where this En is the nth elementary symmetric function. And this mysterious operator, nabla, is an operator acting on the ring of symmetric function, and it acts by an eigen operator to the modified McDonald polynomial with the eigenfunction T mu. And this nabla operator was first introduced by Bergeron, and it was first written in a paper of Bergeron and Garcia, where they studied the science fiction conjecture. So this nabla operator came with the science fiction conjecture, but it took another way, and it was used to describe this graded Frobenius characteristic of the diagonal coinvariant algebra. And as I mentioned, the dimension, the n+1 to the n-1, is computed, this number is counting the number of parking functions. So there might be a way to describe a combinatorial formula in terms of parking function. And that was what Carson and Mellett proved in 2018, and it's called shuffle theorem. And it was originally conjectured by Hageland, Heyman, Lohr, Remo, and Ulyanov in 2005 paper. So it took more than a decade or so. What this conjecture or shuffle theorem says is that this nabla sub en is dn, which is a generating function of q to the dinv, the diagonal inversion. I'm not going to define this one. And t to the bounds, and f to the inverse descent of w, where the sum is over all parking functions of length n. Okay. So there's a way to define these functions and parking functions in a way, and to give this combinatorial formula. And they proved that this combinatorial formula coincides with this nabla sub en. Okay. And since then, there are various fascinating directions to take this nabla sub en or Qt Catalan numbers to other found in other areas of mathematics, like knot homology or the Hutch structure of Richardson variety or something. I'm gonna mention a few generalization of this shuffle theorem, which is one is rational shuffle theorem, which was proved by Mellit in 18, and delta theorem, which was proved by Mellit and Michael D. Derio in 2022, and Heyman, Morse, Lasha, Kuhn, Sillinger in 23, or very generalized version, which is Rohr-Warrington conjecture, and it was very recently proved by the same group in their preprint. Okay, and we're going back to the science fiction conjecture. So our result, it's not on the archive yet, and we are writing this up, and we think we are almost done, maybe in 2 weeks. So consider the same situation in the science fiction conjecture. So take a partition of mu plus one, n plus one, and take k distinct partitions inside mu, such that the differences are all one. What we have proved is first thing is what we call the vanishing identity. And so for m, which is less than k minus 1, then we have the McDonald intersection polynomial skewed by e n minus m part is 0. So here, this skewing operator is a joint operator to the multiplication of the elementary symmetric function with respect to the whole inner product. And the second assertion is connection to the nabla sub en. So we give the same calculation, but for this time, we give we have equal here. So e n minus k plus 1 part to the McDonald intersection polynomial, it gives some scalar intersection of t sub intersection of all these partitions, and then nabla sub en. Nabla sub ek minus 1. And the third is almost the same thing. So it's connection to the dn, the combinatorial formula for the shuffle theorem. It states that this McDonald intersection polynomial skewed by this operator gives the same scalar and the combinatorial formula bk minus 1. So as a corollary, we get the shuffle theorem by combining these two, B and C. And I have 1 minute. So one thing I'm gonna talk about is we have also gave a recall that the McDonald polynomial at 1 was Q and T equals to 1 was H1111, and McDonald intersection polynomial of 2 partition at Q and T equals to 1 was H21111. So their H expansion is very easy. And we observed that the same phenomena happens to the general McDonald intersection polynomial. So McDonald intersection polynomial at Q and T equals to 1 has very nice H expansion. So it's over all partitions of K minus 1. And it involves some sign and the Crowder's number, which counts the non-crossing set partitions or the thick path of certain condition. And then H. This one, okay. So it has very nice H expansion formula. Final remark is that if the science fiction conjecture is true, McDonald intersection polynomial without specializing this should be sure positive. But for now, we don't know how to prove it, and we even though we know how to expand McDonald intersection polynomial at Q and T equals to 1 in an H basis, but this involves some signs, and we don't know how to prove that this symmetric function is sure positive or even monomial positive. So I think this problem is very interesting problem and may help to understand science fiction conjecture more. Okay. This is all I have for today, and thank you for listening.
Thank you very much, Jaeseong. Well, in regard to this last one, are you saying that you do not have a monomial positive formula for the left-hand side here?
No, I mean for both. I mean, yeah. We don't know how to convert this formula to the positive monomial formula.
Oh, so even when Q and T are 1,
No,
that's
no.
hard.
Yeah,
Okay.
I mean, all I'm saying is we haven't proved it. So I'm not gonna say this is hard, but I think it's hard. But yeah, who knows?
So
Can
does
I ask
anyone
a
have any
question?
questions?
Yeah, can I ask a question?
Yeah, sure.
Yeah. In this expansion, I have 2 questions. One of them is in this expansion where you have the Crowder's numbers. This expansion involves all partitions of K minus 1.
Yeah,
They all have to be present.
yeah.
Okay. The next question is up 2 or 3 pages up, back, I mean. Yeah, where you had 1-1 case, the case 1-1.
Oh, maybe this
equal to
one.
1. Yeah, this one.
Yeah.
In here, if I may, I want to ask one question. One, your claim that you have sure positivity when when you have Q and 1, and by symmetry 1 and T, you have sure positivity. What about, since you don't have it in general for Q and T, what about when it is Q and T is 1 over Q?
Oh, we haven't thought of it seriously yet. Oh, I mean, yeah, I to answer the question, I have to mention some of the proof. I mean, the HHL formula is F expansion, but it also gives an LLT expansion. And if you specialize one of the variables to one, you can only considering the LLTs, not considering all the other stuff. And then we could use sure positivity of the LLT polynomials. That's how we prove this sure positivity. So specializing one of the variable to its inverse, I'm not sure. I mean, our technique does not work for sure, but we haven't thought about it yet.
Okay.
One of the interesting things about the QT Catalan and the Nodley EN is when T is 1 over Q, everything kind of simplifies greatly. You have very elegant combinatorics. But somehow that no one's ever figured out how to do that for the QT Cosca when T is 1 over Q.
Oh, yeah.
It's been the somewhat disappointing.
Okay, thank you both. And last question is, earlier you had h1 to the power of n, but in this case, in your theorem on this page, you have, for the 1-1 case, you have a 2. Actually, is there any conceptual reason why there is a 2?
Okay.
I mean, an easy answer if you can give.
Okay, so coming from this formula, it's lambda mu is 1 is over partitions of 1, and h1 plus 1 to the n minus 2 gives, and Clover's number is 1, and the sign is 1, and this will give you h2 1 1 1 1 1. And another reason is that so we are considering the situation like this, and the science fiction conjecture asserts that this one is the same with this one, with the operation called flip. So flip lambda, and flip involves some QT reversal and omega, the involution of the symmetric function. So and once again, the n factorial over 2 conjecture asserts that these two are the same. I mean, of dimension n factorial 2, and a natural way to divide permutation into 2 same size pieces is by considering the first 2 numbers, right? If the first number is larger than the second number, or the first number is less than the second number. And if you take the generating function of those permutation, you get h21111, and its omega image is e21111. So that's why we come up these. But if you involve Q and T, that's not simple at all. But yeah, in a sense, yeah. And that's why this question is hard for me, because there's a way to divide the set of all permutation into 2 exact same pieces, but we don't know how to divide it like into these 4 pieces. I mean, there is no natural way to do this, and if you find a way, you can. I think we can give a formula, monomial or sure expansion for this one.
Thank you again.
Thank you for the question.
Other questions? Okay, I guess not. Then, well, thanks again, Jaeseong. That was a great introduction, overview, and thank you. And we'll see you, I guess, all on Thursday.
Oh, wait, this Thursday?
Yes.
Yeah, 2 days later.
Ah, okay. I could actually make that one too.
Mhm.
Cool.
Cool.